The U.S. wants to develop a new type of nuclear weapon, a nuclear earth penetrator or bunker buster. This nuclear bomb, intended to destroy underground targets, would be useless against many bunkers. At the same time, it would produce massive amounts of radioactive fallout and potentially kill millions of civilians. The nuclear bomb, dropped by an airplane, would only penetrate a few meters into the ground, too shallow to contain the nuclear blast or the large cloud of radioactive fallout. The nuclear radiation could spread more than 1,000 miles. If the United States used a single weapon with a 1 megaton yield against the Isfahan nuclear facility in Iran, for example, the deadly radioactive fallout would spread to Pakistan, Afghanistan, and India. In this simulation, based on a model developed by the Pentagon, over 3 million people would be killed as a result of the attack, and 35 million people would be exposed to significant cancer-causing radiation. To destroy buried targets, the seismic shock wave produced by the bomb would need to reach the bunker. However, a 1 megaton nuclear bomb with 60 times the power of the Hiroshima weapon could only destroy bunkers within about 1,000 feet of the explosion. Very deep bunkers can be built with modern tunneling equipment, and the United States is unlikely to know the exact location of bunkers even if it knows the entry points. A nuclear weapon would also be ineffective at sterilizing underground stockpiles of chemical or biological weapons unless it detonates very close to the target. This is because the heat and radiation from a nuclear explosion do not travel far underground. If the weapon doesn't destroy the stockpile, the explosion is likely to spread active chemical or biological agents into the environment, in addition to the radiation. A more sensible way to deal with the military challenge posed by underground bunkers is to use precision conventional weapons to attack all entrances and exits to the bunker. This would keep chemical or biological stocks sealed underground and prevent enemy personnel from entering or exiting the facility.
Because we do have much more capable weapons in our inventory.
At Eglin Air Force Base in Florida, the United States tested a new superweapon. MOAB, short for Massive Ordnance Airburst, quickly became known as the mother of all bombs. This massive weapon creates a blast radius stretching a mile in each direction.
The MOAB is made out of an aluminum skin, a very thin aluminum skin. And the reason we did it that way was in order to maximize the blast effect. We did not want the airframe of the bomb to interfere with the development of a blast wave that has the impact to the target.
The world's largest non-nuclear weapon, MOAB is over 30 feet long and weighs more than 21,000 pounds. It's no easy task to accurately maneuver such a behemoth through the skies toward its target. Engineers overcame the challenge with a grid fin design that provides great aerodynamic lift.
During carriage, these 4 grid fins are folded forward onto the bomb in order that it makes a very compact design for carriage. When the weapon is deployed out the back end of the C-130, the fins are subsequently deployed with aerodynamic assisting in the deployment because the wind is coming from the forward of the bomb. Once it's in its flight configuration, as it is shown here, it is then able to control the bomb and fly it to its designated target.
Although MOAB was fast-tracked for Operation Iraqi Freedom, the lack of enemy resistance kept it grounded. But its successful test run served chilling notice of a powerful new force.
The largest guided bomb in the history of the world, with the tremendous impact and detonation of this explosive, really just shook the area. And the shockwave could be heard for miles and miles.
The Palace of Versailles in 19th century France. Gardener Joseph Monnier builds big, strong concrete pots to plant trees in. Only there's a hitch. Trees grow and expand, but concrete is rigid. Monnier needed to create concrete that could stand up to the power of plants. I've come to meet engineer Gareth Hughes to find out how he did it.
Gareth, probably the best way then to understand what concrete is to make some, so I brought a wheelbarrow and a shovel. So what's in it?
The basic ratio would be 3 coarse aggregate, 2 sand and 1 shovel of cement. That's what gives it its strength.
Finally, you need water to bind it all together. That's basic concrete.
So what's wrong with it? I mean, it is immensely strong, surely.
It is strong, but only in certain applications. For example, if someone was to squash it or put it under compression, then it's very strong. It'll resist that force for quite a while. But if it was to have something that was going to be in the middle, say, a heavy load in the centre of it, it could bend it, put it in tension. And it's not very strong under those circumstances. It's quite brittle and it'd probably snap.
So like any material then, it can be very strong in one way. In this instance, you can't squash it.
Yeah.
But if you try and bend it, that's its weakness.
And that's the problem with ordinary concrete. The concrete in the troll needs to be able to give to withstand the constant pounding from big waves. Gareth wants to show what would happen if it were built of ordinary concrete. First, we have to build our own concrete test lab. We know ordinary concrete is very strong if you try to compress or squeeze it. We're going to see whether it will bend. In other words, what tension does to it. Gareth has prepared a huge slab of concrete, 8 inches thick and weighing nearly 5 tons. You'd think this would be incredibly strong. Let's see. I'm going to drop a small 70-pound weight just 10 feet, the equivalent of a 13-foot wave hitting the trolley platform. Surely, if the troll were made of something like this, it would stand secure.
You would have thought concrete of that thickness would be pretty strong. I know I did. And it is. It's just that it's only strong in certain ways. It does have weaknesses. I can't believe that broke it.
And this was Joseph Monnier's problem back in 19th century France. He found the pots cracked as the tree roots grew and expanded.
Monnier's solution was to add a reinforcing material that could bend and stretch and make up for the shortcomings of concrete. In his day, he used iron. Today, we use steel, but it's exactly the same theory.
And it's beautifully simple to make. Just pour concrete around a steel frame. Reinforcement lets the concrete bend, and concrete protects the steel from the elements. This slab is the exact same size as the one we just broke. It's still 8 inches thick. The only difference is that it's been reinforced with 26 steel rods. To test it, we're not going to mess around with the kind of weight I can lift.
That's the slab that broke. That should weigh a bit.
Whilst we can't drop a 5-ton skip, this will be 50 times the load of the earlier test. But will some thin rods of reinforcing steel really stop this slab from breaking?
Technically, this should work. Technically. If it doesn't, could hurt.
It's holding for now.
The only difference between that slab and the one that broke are those few bits of reinforcing steel. This is the gauge of steel that they used to reinforce that slab. And this is the gauge of steel they used to reinforce the concrete on the trolley platform. That's got to be tough.
As Monnier found, you don't need much steel to make it effective. But because Troll is so huge, there's still enough steel for 15 Eiffel Towers.